Okay. Well, first of all, I would like to thank you, all the organizers, to invite me here and have a chance to present my work. I feel really honored after, especially yesterday's sightseeing. I was really overwhelmed by the history that is directly connected to the present of Israel. So I was trying to start with a joke, but since we are delaying our lunch, I will not. Okay. Instead, I'm going to introduce my institute. We spent a few minutes to introduce my institute. So this is the eastern part of the world. You will probably recognize where it is. This is China, and this is Japan. We are in between Japan. And on closer look at this area, we have the peninsula is divided into two, and we are from South Korea. Okay, and even closer looking at it, so this is the city, capital city of Korea, Seoul. And my institute is at around 30 minutes below down south of the Seoul, so it's close to. And then this is the way the far view from to our institute. So I was thinking, what would be the impression, the best reminder of our institute for those who are not familiar with institute? I was thinking two things. One is our university is the oldest one. If you don't remember the name, then you can Google what's the oldest university in Korea, then you will find my institute. And the second one is the Samsung run, so it's owned by, our institute is owned by Samsung. So that's one of two things that I can brag about. And another thing that I can show you is so this is a global ranking, and what it tells us is that, well, the Sangjun University is ranked 68, comparable to, let's say, where is it, Johns Hopkins University. Believe it or not, that's what it is. And then it's also recorded in 2016. I'm pretty sure that we are lowering currently, but that's the best out of our history. So yeah, I guess I want to say that Sangjun University does better than the reputation, I guess. Okay, so I'll come back to science. So what I'm going to do today, well, I'll briefly introduce topological phases of matter that is relevant with my work, and then I will basically summarize two main ideas that we did in these two papers. So if you want to see the details, interested in the details, you can confer to these papers. But what basically I want to deliver today is that twisted biolographine can host so-called higher order topological insulator. And the second thing, the topological insulator, the higher order topological insulating phase can give rise to something measurable. I'm not sure it is quite convincing, but I'm trying to convince you with this. And then before going into the details, I would like to introduce my collaborators. First of all, these two works, so you see this park, we have many parks, I already commented this before. We have many parks, Kim and everywhere they park, they are not a sibling or any. But so, and I'm trying to tell you that the first park is Munchi Park at IBS, Institute of Basic Science, Center for Theoretical Physics of Complex System, and also Hichol Park is here, and Jo is present. We are collaborating. This is a big collaboration in Korea. So, and Songbin Lee from KAIST, and my student Sunam Jeon from Sangjun University. Okay, so I'll go into detail. So before I go into the detail, I will briefly introduce the topological phase. So I'm pretty sure most of you already know this, but I would like to briefly summarize what I want to deliver. So topological insulating phase is characterized by bulk topological invariant, and then invariant gives rise to physical manifestation, which is a boundary topological mode. Archetypal example is 2D integer quantum effect which has a material version. It's called quantum anomalous Hall insulator in 2-dimension or even 3-dimensional Chun insulator. Whatever it calls, the consequence is that the bulk has an integer Chun invariant defined in the bulk. So and has a boundary consequence as a chiral edge state for this particular phase. So if, let's say this is a bulk, then there is a localized state at edge, and in momentum space it appears as the chiral the localized state on the edge like this. And then well, this story has become much in niche since 2005 by symmetry. And then the first example of symmetry-related or symmetry-initiated topological phase is time reversal version. You can simply think this is the 2D topological insulator is archetypical one, and you can simply think this is a double copy of two quantum Hall states, so people call helical states. You have two edge mode due to the non-trivial G2 invariant in the bulk, which one goes to right direction and the other one goes the other direction with different spin, majority spins. Okay. And then obviously it can be extended into higher version as a 3D topological insulator. And this 3D topological insulator is characterized having G2, there is a specification called weak invariant, but basically what it tells is presence of non-trivial topological invariant calculated from the bulk, the inside of the material properties, give rise to the surface metallic state, although the inside is insulator. Due to the presence of non-trivial G2 invariant, there is a metallic state on the boundary, which is exciting. And the metallic state is special because it looks like a 2-dimensional Dirac cone. Has an energy momentum relationship that looks like a Dirac cone. Okay. And then later, there is an extension of this idea into a semi-metal version. So again, the representative example is by semi-metal. So what the idea is in 3-dimensional Brilliant zone, so it's a momentum space. So energy, momentum, it only looks like linear. It's a 3-dimensional space, schematically drawn. And it has a doubly degenerate point that is linear dispersion away from this point in all 3 dimensions. So the low energy effective theory should be written in this way, linear dispersion without gap. It's a famous effective Hamiltonian known as a bi-Hamiltonian. So people call this as a bi-point, and it is characterized by having a non-zero Chern number calculated over on the 2-dimensional boundary that encloses the bi-point. And this is a somewhat not as famous, but the graphene also can be considered as a topological semi-metal in similar sense. So the graphene is a famous material made of carbon atoms in honeycomb lattice. And in the energy momentum space, the electrons, the quasi-particles living in this graphene has a linear dispersion. And then you might wonder why there is a linear dispersion. So one answer to the question, just the stability of the Dirac point, the linear Dirac point, can be answered this way. So the system preserves 2 symmetries, is the inversion symmetry and time reversal symmetry. And the absence of spin-orbit coupling, which is a very good approximation in this carbon atom system, give rise to this condition t is equals to 1. And what end up with what these conditions give rise to is the reality condition or quantization of any phase, any Berry phase, or well, it can be Zak phase. So the phase that is calculated along this line that encloses the Dirac point. So it gives pi. So this symmetry and a rollable absence of spin-orbit coupling quantizes the Berry phase that is calculated at any circle, any closed loop in the 2-dimensional momentum. And whenever it encloses the Dirac point, it gives pi. And whenever it doesn't, then it gives 0. So in this sense, similar to the Chern number that has a non-trivial Chern number whenever the surface encloses the bi point, this point is protected by this periphase. So we can think of this periphase is topological invariant that can be considered as conservative charge given to this point. Okay, so in a fancy way to explain is, this condition gives rise to the reality condition, and unlike the Chung class, there is a Stipalbutini class that is characterizing the real vector field, and we can apply that concept into this example, and the periphase corresponds to the first Stipalbutini number. Okay, and the good thing though is that, well, whatever we call, the good thing is that we can extend this mathematical concept into higher version, like a second Stipalbutini number, third Stipalbutini number, and that's one of the directions that we are pursuing. But I'm not going to go into that. Instead, I will present the twisted bilayer graphene. So this is a real space view. So see that something is rotating. That's one graphene sheet on top of the other one. So it's a bilayer graphene, and it's rotating. And as you see, there is something going into and out, depending on the angle. And then you immediately find that, well, the translational symmetry depends on the rotational angle. So what you can do, you can change continuously something, and then drastically change the material's property as a function of an angle. So this is quite interesting to see this. So this paper in 2012 reports the many degrees of twisted angle can actually exist in nature. And I'm pretty sure this is 2012, and there's much more progress in this synthesis-wise work. And depending on what is interesting about the bilayer graphene, twisted bilayer graphene, personally for me, is that, well, as I said, we continuously change something, but their consequence is very drastic. So this is a sort of fake, when we actually, it's very easy to do graphically, but if you think about you change the film of your cell phone and rotate it, it takes really large energy. That's the van der Waals interaction between the screen and the film of your protecting film of your iPhone. And you can take off easily, but you can rotate it as it is attached. So that's what I'm actually doing here. So if you do that, then it takes a lot of energy and changes the electronic structure drastically. So the consequence is, first is this, the correlated insulating behavior, which is people consider it will not appear in graphene system. So it is usually a transition metal atom that is involved in this correlated insulating behavior, like mount insulating behavior. But this light atom graphene gives rise to this mount insulating phase and unconventional superconducting phase, just because we twisted it at the right angle. And interesting direction that was published in 2018 from our department is exact 30-degree angle. So if you think about the symmetry, and what this 30-degree angle breaks completely the translational symmetry and generates the so-called Cauchy crystal. So it is surprising that experimentalists actually set this exact 30-degree angle and found the many replicas of Dirac point from the RPS data, which is exciting direction. Anyway, what I'm going to say today, though, I will focus on different angle. I'm literally the angle. So I'm going to go to the large angle limit and find the topological properties, and I'm trying to use them for electronics. So let's see if it really mean it. Okay, so twisted bilayer angle that I'm interested in is the angle that 21.78, which is large angle. It's a different angle than the magic angle, which is usually very small. So why am I interested in this? Is because this angle gives the smallest unit cell that is other than just a zero rotation angle. So I want to have the smallest unit cell. See this, the bright dots coming inside and outside, the bouncing of it, and then depending on the angle. So this pattern is corresponding to this circle, look like a pattern here. and they are repeating. So obviously the unicell looks like this. And this unicell contains 28 atoms inside. And see this blue dot and a red dot distinguishes the layers. And a blue dot is upper layer, red dot is a down layer. And why you want to have a small unicell? Small unicell can have a chance to see opening a gap. So I have nearly 2 decoupled graphene bands that is folded into the moire Brilliant Jeon. But if I close a look at it, and this is calculation done from the LDA approximation using density functional theory, standard density functional theory calculation, and I found that the few electron volt gap. Okay, so this is unlike the magic angle graphene, which has a flat band at the 0 energy mode. Okay, so I'm going to take advantage of this band gap, okay, and claim that this band gap results in a higher order topological insulating phase. That's the one part of the story. So what I can do, I can just prepare this flake. You see this the small dots is actually meaning this point. So you immediately know this is a large scale system. And I do the calculation of density of state using this large flake and found that, well, obviously the bulk will live in the energy window that is occupied by these bands. And I have this tiny band gap. Well, this is a very small band gap. There is band gap. And I found that localized state lives inside of the band gap. And picking up this state and draw in real space, I found it is localized at the corner like this. Okay? So finding, we found corner localized state that lives in energy window in the bulk gap region, and I want to convince you that this localized state originate from bulk band topology from now. Okay, so how we can do? So by the band bulk topology, I really mean the second order in 2-dimensional higher order topological insulating phase. So in 2017, by these people, the idea of topological insulator has been extended into multiple orders. So what I mean by order is the dimensional difference from the bulk system to the boundary consequential space. So for example, in 1 dimension, well, I will have the best example, 2 dimension. In 2 dimension, people have known that due to the bulk in 2 dimension topology, there is a edge mode that is localized as a 1-dimensional boundary. But what higher order, especially in second order, means it is not the boundary, but it's a corner that has hosts the localized state due to the presence of non-trivial topological number that is defined in the bulk. Okay. Yeah. So I'm a little bit worried about because of the comments that is raised by Professor Lek. So I'm trying to take advantage of the Josh is sleeping, but yes. it's a good introduction. I'm sorry, I thought you would do. But your introduction of Zak Phase, I really, well, it's the best introduction that I have seen. But I'm trying to use the Zak Phase and then characterize the presence of localized states. I'm afraid that he's going to say that's not a topological invariant. We can discuss later. Okay. Okay. Yeah. Yeah. So I will continue anyway. So this concept can be extended in the multiple dimension, like 3 dimension. You can have a second order, even a third order. Yeah, and then Sangjun introduced this version. I'm not going to detail, but I would say that the graphene flake has a localized state due to this type of topological insulating phase. Okay, how I can define? So how can I define it? I'm going to calculate the Zak phase. Yeah. So I have many symmetries that is preserved by the real space system, like C2X and C2Y, and I have more, but these 2 are most important symmetries that I have. So I'm going to detail you. So I can rotate this system with respect to this axis. Then you will see this blue dot will go to the red dot, and that means I'm distinguishing, but these are all carbon atoms, so I cannot distinguish this rotation, so it preserves symmetry. The consequence of this symmetry is in momentum space is the invariance of wave functions. Wave function respects this symmetry by having well-defined eigenvalue of this symmetry. Then what I can do, I can focus on the block Hamiltonian living along this line and block diagonalize the system into the C2x plus and C2x minus space and calculate the Zak phase independently from one sublattice, one subspace group, space block, and find the Zak phase is non-zero. Okay. So what's the consequence? Yeah. So the consequence is in the bulk, using the bulk state to calculate this Zak phase, I am having a non-trivial number. So the consequence can be an edge state living at the boundary. So well, one might wonder why there is a protective state. It's not protective. It's not topological in the sense that the purpose Oleg mentioned. But I'm trying to tell you that, well, due to the fact that my plus sector and minus sector have independent two Zak phase, I have two surface localized. In this case, the surface means the edge localized metallic state that goes one direction to the left and then the other one to the right. So plus eigenvalue Zak phase dictates the presence of the left going edge state, and minus Zak phase dictates the edge state localized at the boundary on the right-hand side, going right-hand side. But since I have two states at the boundary, this is not robust. It's not alone the Zak phase itself, but the presence of these two phases is always susceptible to any perturbation that breaks this symmetry at the boundary. So I can always open this gap, which is a good thing to me. So what I'm going to do, since I have Zak phase, and then that plays the role of two-dimensional system localized on the one edge, and then I can make a construction of Schrieffer-Higo chain that is, in this case, is bent. So I have a plus mass gap state on the one boundary and the other one at the boundary, and have the band gap inversion through this corner. So that is the reason why we can see the corner state at the boundary. It's a zero mode, the Schrieffer-Higo chain that is bent on the boundary. Okay, so just the presence of edge state due to the C2 reserved Zak phase, I can host a metallic state at the edge onto edge, and since this is susceptible to the boundary geometry, I can open it, and I can open it such that using another symmetry that is preserved by the system, I can open it such that the plus minus eigenspace is switched by having this symmetry transformation. Okay, so that means I can have the mass gap inversion from this edge to this edge, and this point host to the Schrieffer-Higo zero mode. Okay, so that's the explanation why they exist, and this all topological number are calculated from the bulk, so it's obviously from the bulk property. Then when we do this, have done this project, and my experimental colleagues, yeah, sure. This one? So sorry, I didn't hear.
Why you have these corner states on the top? No, second slide. Next slide.
This one?
No. Next.
This one?
No. Next slide.
Next.
Yeah.
Yeah.
Why it's on the top and the bottom and not on the corner?
Yeah. Since this edge is symmetric to this edge, I have another symmetry that transforms from here to here. So I have two independent states, in fact. Okay. Right? Okay, then so we thought about the functionality. So every time when we propose something related with topological materials, people ask about I can do with that, and how can I come to see the manifestation of a topology. So we thought this system. So this is the system that I just showed. This is a flake of large system of twisted bilayer graphene, and we made this geometry by having two ribbons that is overlapping with this region. Okay, and why we did that? We consider this as a source and drain. So electron can be incident from this direction and flow out of either three of these terminals. Okay, and then want to calculate the resonant tunneling probability from coming this one contact 1 and to contact 2, which means it should transform from the upper layer to the lower layer. Okay, so what's the consequence? The consequence is before we show the transmission probability, what we found is the corner state, since we have finite size, the corner state start to talk each other and give rise to the hybridization. Okay, so it lives at different energy. So if I plot the wave function of this state, then we'll localize the one and the other one will, but their hybridization non-zero give rise to this splitting of energy. And then what we do, we apply the gating on this region and found that this corner state is oscillating. Okay, it's a sort of corner oscillations. So due to the hybridization. What is surprising though is that if it is localized, trivial localized state, then we will not talk each other, and the applying electric field will just run this state into either one direction or other direction, just like these states. This state goes in one direction. It doesn't go to the other direction. So if the state feels the electric potential difference, and then if we increase one direction, the potential is increased, then we thought that we will go one way or the other, but it oscillates. It's a quantum effect. So we wanted to answer the origin, and this is what we found. So we simply modeled the system as the two state that has a metally connected state. Okay, so it's a one-dimensional system. So one state lives at the theta equals to 0 point, and we model this point as a theta equals to pi point. This is drastic approximation, modeling this system as a circle. But we believe that the essence is captured here. So as Joseph introduced, what we pick up here is a phase that is transported from 0 to pi state, here to here. We parallel transport the electron from this side to this side, and then subtract it with the other guy who leaves this one, or the other way, that travel the other way. So, and find that the phase difference is directly related with the gate voltage, linearly dependent on the gate voltage. Of course, it also depends on the size of the flake. So what we found, the physical meaning is that this gate voltage plays a role of Berry curvature that is felt by by these two electron paths traveling around this region. So that explains the phase difference, and then the phase difference gives rise to this oscillation. And what is interesting here is that when they are completely decoupled, or their path is completely dephased, the interaction becomes 0, and then what end up with this is the transport calculation is that we have resonant tunneling. So when electron comes in this direction and flow out of this direction, it can have transmission, non-zero transmission, only when electron can have a resonance with this state energy or this state energy. So it picks up the energy of the corner state and the oscillation.
Can I ask a question?
Yeah. Sure.
Is this dependence of the gate electric field connected to the polarization?
The Berry phase. having a rollover vary phase. So it's just like Aharon of
About the charge polarization
charge polarization at,
of the system.
sorry?
If this electric field dependence is related to the polarization of the electrons in the system.
Electrons in the system, polarization. So,
Charge polarization. So we haven't considered the charge polarization and the consequence on the potentials, but so what we are doing, so I guess the charge polarization will do, so in this calculation we didn't include it, but I'm thinking what will be the consequence of charge polarization? That will change the effective gating potential. So the top layer and the bottom layer will see the different potential. And depending on how the system reacts to the external electric field and the formation of a polarization, this state can have, well, not this pretty running, but still I believe because the polarization change is eventually changing the gating value, the oscillation will still appear. Okay. Oh yeah, so nearly the end. So well, it is natural whenever the metallic state is meeting the localized state, the metallic contact meets the localized state, it can transform due to the resonance. But what is non-trivial here is right at the node, the transmission becomes 0. That is a reflection of the absence of hybridization here. So electron cannot jump from. So unlike the usual transmission, there could be sudden node and absence of transmission here. That's something that is not expected from this geometry. So this is pretty much the end of the talk. So I want to convince you with these two messages. The first one is a higher topological insulating phase can live in twisted violet graphene, but there are much details. But we believe this could be possible. And then second one, higher topological insulator phase can give rise to some new phenomena that has been not appeared in with the regular normal state. So that will be the end of the talk. So I will be happy to get your questions. Thank you.
Thank you very much. Any question, please?
Yes.
So I'll start with the questions. My question is with respect to the last experiment with these cross-shaped ribbons. So first question is whether you are assuming a 2178 angle, in this geometry as well.
Yes.
Yeah. And the second question, you specifically wrote that it's a 7 nanometer width, which is a very, very narrow graphene channel. What happens if it's wider?
Yeah, so this formula tells you what happens. If you reduce this R, this is the size of the flake, then phase change will be very, very tiny. So still happen, but you need a large gating to see this phenomena. So we thought of do the compromisation. Okay, so you raise your hand.
In the picture when you show the edge mode,
this one, or you want to go beyond this one?
yes, in this one. So you take the edges of both layers to coincide. But what happens if they don't coincide? If it's a transition between twisted bilayer to single layer instead of vacuum, do you still have these modes?
No, I don't think so. So what we'll host is first of all the closing of a bulk gap. So we don't have insulating phase anymore. If you decouple the two systems, you can do the Gedanken experiment. So if suppose you gradually detach the two layers and make it into independent two layers, then you will just see the graphene. And then the consequence should be the closing of the gap here. And there is nothing that can calculate the topological invariant related with the topological insulating phase. So this then we can also think about what will happen on this state. I'm pretty sure the localized state in the gap has a localization strength that depends on the bulk gap. So if you reduce the bulk gap, then what you end up with is a delocalization into the bulk. So if you gradually turn off the interaction between the layers, then you will see this state will gradually become a metallic bulk state, penetrate into, and you cannot distinguish it from the bulk state. Does it answer to you?
Gradually make the interaction weaker. I mean, let's say one of the layers is much bigger than the other. So the edges, instead of having both edges of both layers with the vacuum, you have only edge of one layer, but the second layer keeps on going.
Yeah. So again, that will. Yeah, let me rethink the answer that I'm going to tell you. So the bulk state happens because of the hybridization of the edge state. And if you increase the bottom layer, for example, then you kill one state at the edge. Then, well, you ruin again the gap. So gap happens due to, here's the distinction. What I'm trying to tell you, I have already the bulk gap, but this bulk gap induces the localized state, the edge localized state. And I'm talking about this edge state. I'm opening the gap again to induce the corner state like this. And now you're losing the gap opening by increasing the bottom layer. I think that will happen. Does it answer to you? Are you satisfied?
I will still have the edge state in this case?
For one state. And that can be, well, easily ruined. That's coming from the Zak phase. Zak phase that is susceptible to the choice of units. So it doesn't guarantee. So that there isn't a topological number that guarantees the edge state. But well, starting from the presence of edge state, I can imagine that one is killed, and then the other one just open the gap. Cannot open the gap. Right.
So we may have time for maybe one question. So Yuval. Oh,
maybe our guest.
Yes, our guest, please, and then Yuval, and then we can.
I think this is very interesting result because by rotating, you introduce kinds of some phase by physically rotating the system. Then my question is, usually when you apply the magnetic field, you have some kind of quantum flux, quantized flux, something like that, so that you can, anyway, that is, for example, Josephson junction is a good magnetic sensor.
Right.
In your system, seems like this system is a very good electric field sensor. You can use this one for very sensitive electric field sensor. In that case, can you imagine some kind of quantized kinds of electric field quantity you can extract from here, like magnetic quantum flux here? Something like electric version of quantity of quantum analogy.
So yeah, I think there are too many obstacles to go to the actual sense. So, but I think that's a great idea, especially for the functional topological insulator phase. Think about it. But well, so the first obstacle that I have in my mind is the weakness of the to use a sense. You have to be a sensible sense, but for regular electric field, it cannot open drive this. I mean, this is related with the chairman's question. I use this, specifically use this size of the system to reduce the gate strength, but in reality, I don't think the sensor is possible. Sorry about that. Okay.
noch ziehen wir Osvim. Okay.
I have many errors.
Next.
Next.
why they go in one direction? These red and
why
there is no backscattering?
Okay, so it's not. It's a schematically drawn. That's a good point.
There is backscattering in the corner. Right?
No. I have a multiple channels. When we calculate the transmission coefficients, we apply the Feynman approach of scattering problem. So we have virtual paths that goes one direction and the other direction.
Yeah.
So I'm schematically drawn this figure, but there is a virtual path that goes.
There is backscattering in the corner, for example, as well.
In phase. It's not actual backscattering. It's a virtual path that gives you a backscattering phase. Does it make sense to you? Yeah. Okay. Right then.